we have an equation x squared y prime equals to y squared plus 2xy. So first we will replace this. So as you can see, we can solve it using the homogeneous differential equation. So we'll let y equals to ux dy since we replace the y prime into dy over dx, so we have dy over dx u plus x du over dx. So we substitute y equals to ux and dy over dx equals to u plus x du over dx in y in our equation and dy over dx. So we have so factor out x squared and multiply it by 1 over x squared so that we can cancel this x squared. So in this equation, we can use the separable differential equation. Then we will separate this and integrate it. As you can see, we can easily integrate this, but our du over u squared plus u is we still use the partial fraction. So we will solve partial fraction. And our target is to find the constants for a and b. So we have a equals to 1 and a plus b equals to 0. So we have b equals to negative a, which is negative 1. So we have a equals to 1 and b equals to negative 1. Since we have a equals to 1 and b equals to negative 1, so we have du over u minus, since we have negative 1 here, du over u plus 1 equals to integration of dx over x. So we can now easily integrate these equations or terms. So we have ln of u minus ln of u plus 1 equals to ln of x plus c. Since we substitute y equals to ux, so we can get the u equals to y over x. So we substitute u here in our equation, ln of y over x minus ln y over x plus 1 ln of x plus c. So we have logarithm, so we can use e ln y over x times e to the ln y over x plus 1 to the negative 1 equals to e to the ln of x times e to the c. So we will simplify this equation. So we have y over x times x over y plus x equals to cx. So we can cancel y over y plus x is equals to cx. So our target is to get the general solution using y. So we will simplify it more further. So we have y plus x over y, so 1 over cx. 1 plus x over y equals to 1 over cx. X over y equals to 1 over cx minus 1. So we have y equals to cx squared over 1 minus cx. So this is our final answer. We have an equation y prime plus 2xy plus x equals to e to the negative x squared. We are asked to find the general solution. So at first, we will rewrite this equation. So our next step is to make it into our standard form. So we have our standard form. So we will now use the linear differential equation. So we will now find the integrating factor. So we have v to the function 2x dx, v equals to e to the x squared. So our v equals to e to the x squared. We will multiply this from this equation, e to the x squared. So our next step is our function y times our v equals to the integration of this term so we will now integrate this. So let u equals to x squared. So we will have in our equation let u equals to x squared e to the u du. So we will have then our final answer is we have our problem y equals to xy prime minus 4y prime cube. As you can see in our problem, we have an exponent 3, so it will not be easily use differential equations using linear, separable, or anything. So at first we will write this as x dy over dx minus 4 dy over dx cube. In this equation, we can use the Clairaut's equation, so we can have, let dy over dx equals to p. So we have y equals to x p minus 4 p cube. And in our Clairaut solutions, we can let p equal to m, or you can also use c. So we have y equals to m, or you can use c, mx minus 4m cube. So this is our general solution in our equation y equals to xy prime minus 4y prime cube. But we can also get the singular solution. So in our Clairaut solution, the formula for general solution is equals to mx plus f of m, and we have our x equal to negative f prime of m, and our y equals to negative m f prime of m, negative f prime of m plus f of m. So our target is to get x and y, so that we can get the singular solution. So x equals to negative f prime of m. So we will derive this m, f of m, negative 4m cubed, and y. Just use this equation, so we can have x equals to negative of f prime of m, which is derivative of this function, negative 12m squared. So we have 12m squared, which is our x, and our y equals to negative m of derivative of this function, negative 12m squared, plus our function negative 4m cubed. So we simplify it. So we have y equals to 8m cubed. So we have x equals to 12m squared and y equals to 8m cubed. We have x equals to 12m squared and y equals to 8m cubed. So our next step is to equate this x and y. So we have x over 12 to the 1/2 is equals to m, from x equals to 12m squared here, and y over 8 to the 1/3 is equal to m, from y equals to 8m cubed. So we will equate this. So we have x over 12 to the 1/2 equals to y over 8 to the 1/3. So we will simplify it. 8 to the 1/3, x to the 1/2, y to the 1/3, 12 to 1/2. Since this is exponent, so let's multiply it by an exponent of 6. So we have 8 squared x cubed equal to y squared 12 cubed. So we will get 64x cubed over 1728 equals to y squared. So we will simplify this equation. We will simplify this. So we have y squared equals to x cubed over 27, or you can also get y equals to x to the 3 halves over 3 square root of 3. This is your final answer here, or you can also use this. In the problem, we have xy prime minus 3y equals to 0, and our initial value is we have y of 0 equals to 0. So at first, we will solve the differential equation. In this equation, xy prime is equals to 3y. So x dy over dx is equals to 3y. So as you can see in our equation, we can solve this using the separable differential equation. So we have dx over x is equals to dy over 3y. Integrate this two equation. So we have ln of x equals to 1/3 ln of y plus c. So e to the ln of x is equals to e to the 1/3 ln of y times e to the c. So simplify it. We have x equals to cy to the 1/3, then y is equals to cx cubed. Since we have our answer, y equals to cx cubed, and our problem is that y to the 1 is equals to 0 as a solution on negative infinity to the infinity. So we can, using this negative infinity to infinity, we will have y equals to c1x cubed c2x cubed. Since it is negative infinity to infinity, so we have x which is less than or equal to 0, and x is greater than or equal to 0. And if we take c1 equals to c2 is equals to 1, then in our equation y equals to cx cubed, we can get y is equals to x cubed as the particular solution of the problem. So we have the tank. Now the tank, we will rotate it with its axis and get the angular velocity. So in our problem, it is required that the equation, we will find the equation of the curve. So we will have our point here with its corresponding height here. So now we will now focus on the curve. As you can see, we have our point here, which is x, y. So our mg is the centripetal force of magnitude m omega squared x. And our p is a reaction force of magnitude f sine theta equal to m omega squared x over force. So sine theta equal to mass times the gravity over f. So we can now find tangent theta sine theta over cos theta. Mass times omega squared x over force over mass gravity over force. Simplifying it further, so we will have separable equation. We have integration of dy, integration of omega squared x over g dx. So we have y is equal to omega squared x squared over 2g plus c. The equation of the free surface is a paraboloid of evolution with vertex on the axis at y equals to c. So taking the reference point, c equals to ho. So we have y is equal to w squared x squared over 2g plus ho. So our target now is to find this ho. So to solve for ho, we use the volume pi r squared h1, and using the cylindrical shell method, v is equal to 2 pi f of x dx from 0 to r. Distribute the x. So we will integrate this expression. So we have 2 pi our limit of integration from 0 to r. So we have the final answer, pi r squared omega squared r squared over 4g plus ho. And now, we will now equate this to our volume. So we have pi r squared h1 equal to pi r squared omega squared r squared over 4g ho. So we have h1 equal to over 4g plus ho. So now we can get the ho. h1 minus u squared r squared over 4g equal to ho. So substitute this ho. So we have our final answer, y is equal to omega squared x squared over 2g plus h1 minus omega squared r squared over 4g. This is our equation.